Hello and welcome to a new video on IGCSE Classified Physics Paper 4. In this video, we shall be discussing the concept of moments and center of mass. State the two conditions which must be true for an object to be in equilibrium. The first condition is that there must be no resultant force. The second condition is that there must be no resultant moment. In a double-decker bus, there are two passenger compartments, one above the other. A says that figure 3.1 shows a double-decker bus on a tilted platform. The platform is used to test the stability of the bus. The angle the bus makes with the horizontal is gradually increased until the bus begins to topple to the left. Explain why the bus begins to topple. So in the current position of the bus, assuming that the center of mass is somewhere here, we can see that the line of action of the weight, which starts at the center of mass and moves vertically downwards, lies between the two wheels of the bus. However, if we increase the angle more than that, so if the angle becomes like this and the bus becomes like this and the wheels are there, so what happens is that the center of mass shifts to the left like this, and then the line of action falls outside of the wheels. It no longer lies within this black region between the two wheels. So this is the idea. Let me draw another diagram outside to make more sense of this. So in the first case, we have a platform at an angle, and we have the wheels of the bus. And the center of mass is somewhere here. So the weight falls vertically down, and it's still within the base of the bus. It's still between the two wheels. However, if we draw a more tilted platform like this, and we still have the two wheels and the bus, and now the center of mass falls, or the weight falls from the center of mass outside of the circles of the wheels, outside of the base of the bus, outside of this region here. So since the center of mass is not vertically within this region, then this, of course, will topple to the left. So how do we describe this without too many drawings and too many words? We just say that the line of action of the center of mass falls outside the base of the bus. There are 30 passengers in the upper compartment of the bus and 2 passengers in the bottom compartment. State how this affects the stability of the bus and the reason for this. So again, our target, so as not to topple, is for the center of mass to be within the two wheels, within the base of the bus. Now, what happens if we focus so many passengers in this compartment and not enough in the bottom compartment? The center of mass is a representation of where most of the mass is concentrated. So it starts to gradually rise up until it reaches somewhere here. Now, the problem with concentrating the mass in this area is that the weight will fall again outside of the base of the bus. So therefore, it will be unstable and it will be likely to topple. So when we concentrate most of the mass at the top, the center of gravity shifts upwards, center of mass or center of gravity, of course. So it is more likely to fall outside the base of the bus and the stability decreases. State in words the equation that defines the moment of a force. The moment is equal to the force multiplied by the perpendicular distance. If you just write force times distance, you do not get the mark. This is a key word here, perpendicular distance. State what is meant by the moment of a force. A moment of a force is basically the turning effect of the force. Force is a vector quantity. Explain what is meant by the term vector. Any vector is a quantity that has both magnitude and direction. In question B, figure 2.1 shows a tower crane used to lift a load on a construction site. Explain how the counterweight prevents the crane from toppling over. So what happens if there is no counterweight here? If there is no counterweight, what happens is that the load exerts a force in this direction, and this creates a clockwise moment here, and the crane will topple over to the right. But the counterweight produces an opposing moment, an anti-clockwise moment in this sense, and it prevents the crane from toppling over. So how does it do that? By providing an anti-clockwise moment to balance the clockwise moment of the load. In the figure, another elephant is shown pushing horizontally against the vehicle with a force of 11 kilonewtons at a distance of 1.8 meters above the ground. Point M is the center of mass of the vehicle. Calculate the moment about point A of the force exerted by the elephant. So when we are tackling questions about moments, we need to first figure out where our pivot is. So the pivot usually follows the word about. So the moment about point A. So then point A is the pivot. This is our pivot here. We want to see the effect of this force on this pivot. So since the force is horizontal, the distance must be vertical because they must be perpendicular onto each other. So the vertical distance here is 1.8 and the horizontal force is 11,000. And therefore we multiply 11,000 by 1.8 to get 19,800. Of course, 19,800 can be approximated into 20,000. And in scientific notation, this can be written as 2 times 10 power 4, or you could have written 1.98 times 10 to the power of 4 as well. This would have been a correct answer. The mass of the vehicle is 1,900 kilograms, and it does not slide when pushed by the elephant. Determine whether the elephant tips the vehicle over and show your work. Again, our pivot here is point A. Now, we are supposed to take into account the weight of the car. So the weight of the car is vertical, and therefore the distance must be horizontal. Remember, if the force is vertical, the distance is horizontal. If the force is horizontal, then the distance is vertical. Now, the weight of the car is going to be 19,000 because we multiply 1,900 by 10, of course. So 19,000 is multiplied by the distance, which is 1.25, and we get 23,750. Now, this is greater than, of course, 19,800. So therefore, the moment of the car is greater than the moment caused by the elephant, or the moment caused by the weight is greater than the moment caused by the elephant. Therefore, the car does not tip over. Figure 2.1 shows a uniform plank AB of length 2 meters suspended from 2 ropes X and Y. State in terms of P the moment of force P about B. So the moment of force P about point B would be the force itself, which is P, multiplied by the distance between B and the force. And the distance between B and the force is this 1.5 here. So therefore, the moment will be 1.5 P. Calculate the moment of the weight about B. So the weight itself is 210, and the distance from the weight to B is 1 meter. How do I know that it's 1 meter? Because this is 2 meters in total and it's uniform. So the weight must be halfway through. So this distance must be 1 meter. So 1 times 210, and that gives us 210 Newton meters. Now we want to find the force P. How do we find the force P? We take moments about a certain point. Here, they seem to have required moments about point B. So let's just take our pivot at point B and calculate all the moments we want. Of course, Q will have 0 moments because Q is acting at B, so there is no distance to begin with. And the moment of the force P about B is 1.5 P, and this is the clockwise moment here. And the moment due to the weight is going to be anti-clockwise, and it's given as 210. And there are no other forces acting, so all we have to do is just say that the clockwise moments equal the anti-clockwise moments. So 1.5 P equals 210, and we can get P as 140 newtons. Finally, they want the force Q. Now that we have force P as 140, we construct a force equation here. So we have 140 and we have Q. So we can say that F up equals F down, and F up will be 140 plus Q, and F down will be 210. So therefore, Q is going to equal 70. Figure 2.1 shows a uniform meter rule PQ in equilibrium. The distance PQ is 100 centimeters. The mass of the meter rule is 0.12, and its weight is W. On figure 2.1, draw and label an arrow to show the force W acting on PQ at the center of mass. So it's a meter rule, which means it's 100 centimeters in total. And it's uniform, which means that the weight must act 50 centimeters from P. So the weight must act at this point here. And then we want an arrow to show the force R acting on PQ at the pivot. So the arrow would simply look something like this. So let's see the answer. Like we said, the W acts at the middle of the beam and R acts on top of the pivot. In double I, we are required to take moments about the pivot and calculate F. So let's write down our forces and their corresponding moments. Of course, we have clockwise and anti-clockwise. Now, about the pivot, we have W, which creates a clockwise moment. So we're going to write 40W here. Now, the F creates an anti-clockwise moment about the pivot. And the distance from the pivot to the F is 90 because this here is 50. So 50 plus 40 gives us 90. So we have 90F here. And we also have the anti-clockwise moment caused by the weights added here. So we have 10 times 0.5 contributing to the anti-clockwise moment. So we have 90F plus 5. We have 40 multiplied by the weight. The weight is 0.12 times 10. So we have 40 times 1.2, which is 48. This is equal to 90F plus 5. So we have 90F plus 5 equals 48, and then we can solve for F. F equals 43 divided 90, which gives us 0.48 newtons. Now that we have the F, we're required to find the R, and we use the F up equals F down equation. All you have to do is add the downward forces, 0.5, and the W, which are the forces acting down, and then we have R and F acting up. So we have R plus F equals 0.5 plus W. And then we can get R by taking the F to the other side with a minus. So W plus 0.5 minus F. 1.2 plus 0.5 minus 0.48 gives us 1.22 newtons for R. Two mechanics, A and B, are trying to use a two-person spanner to loosen a nut on a large wheel. Figure 2.1 shows the forces exerted by the two mechanics. Mechanic A exerts a force of 500 newtons at a distance of 1.2. Mechanic B exerts a force of 400 at a distance of 1.2 on the other side. Calculate the magnitude and the direction of the resultant moment exerted by the mechanics on the nut. Of course, here they have this force here is 500 due to mechanic A, and this is going to be anti-clockwise. And here you have a 400 force, and it is clockwise, of course. So you multiply 500 by 1.2, multiply 400 by 1.2, you get the anti-clockwise and the clockwise moments, and then you subtract them from each other. So the net moment is 120 in the anti-clockwise direction. Mechanic B reverses the direction of the 400 Newton force that he exerts on the spanner, but mechanic A continues to exert the same force downwards. So now instead of mechanic B pushing down, mechanic B is now going to push up. The issue with that is now that the force, the 400 Newton force, is now also anti-clockwise. So instead of subtracting, we're going to add the two forces together because now they're both anti-clockwise. This is no longer clockwise. They're supporting each other. So now we're just going to add the two moments together and we get 1080 Newton meters. Calculate the magnitude of the resultant force now exerted by the mechanics on the spanner. So the resultant force is F up minus F down or F down minus F up. We don't care about the direction, they just want the magnitude. So you have 500 down and you have 400 up. So you subtract them together and then you get 100 newtons as the resultant force. Figure 2.1 shows a sign that extends over a road. The mass of the sign is 3.4 times 10 to the power of 3. Calculate the weight of the sign. So the weight of the sign is simply mass times gravity. So 3.4 times 10 to the power of 3 times 9.8. And you calculate the weight as such. You get 3.3 times 10 to the power of 4. In question B, we're told the weight of the sign acts at a horizontal distance of 1.8 from the center of the support, and it produces a turning effect about point P. Remember, the word about is a very important keyword in moments because it tells us where the pivot is. So in this case, our pivot is at point P, and this is the point from which we take all our measurements. This is the reference point for the question. Calculate the moment about P due to the weight of the sign. So the weight here is vertical, and we want the moment, so we want the horizontal distance here. We want this distance here. And this distance is simply 0.5 because it is 1.8 minus 1.3, so it's 0.5. And therefore, the distance here is obtained, and we simply multiply the weight, 33,000, by the distance, 0.5, and we get the moment, 16,500, or almost 17,000, or you can write it in scientific notation as 1.7 times 10 to the power of 4. All of these are correct versions of the answer. Now, in double I, we're told a concrete block is positioned on the other side of the support post with its center of mass a horizontal distance of 70 from the center of the support post. State what is meant by the center of mass. Center of mass or center of gravity is the point at which the entire weight of the object is assumed to act. So we just draw an arrow and we assume that the weight of the whole thing acts at this point right there. The weight of the concrete block produces a moment about point P that exactly cancels the moment caused by the weight W. So again, we want the weight of the concrete block about point P. So where is the concrete block? It's right there. And they told us that this distance here is 70, but we want it about point P, so we have to include this 1.3 as well. So 1.3 meters along with 70 centimeters. So let's convert this first to centimeters. We get 130. Now 130 plus 70, that gives us 200 centimeters. 200 centimeters, or just 2 meters for the distance. That would work. Now, since the distance is 2 and we already know the force, we're trying to get the force, excuse me. So the force multiplied by 2 gives us the moment. How do we know the moment? We are told that the moment balances the moment of the weight of the sign. We already have the moment of the weight of the sign. So this is the clockwise moment that we have about point P. And the concrete block produces an anti-clockwise moment about P as well. So therefore, we know that the moment must equal 17,000, and we want to get the force or the weight. So we solve for this, for F in this equation. We have F times 2 equals 17,000. We divide 17,000 by 2, and we get 8,500 or 8.5 times 10 to the power of 3. The concrete block is removed. The sign and support post rotate about point P in a clockwise direction. And this makes sense, of course, because if we remove the concrete block, we no longer have the anti-clockwise moment produced by this block. So the post is going to move in the clockwise direction. State and explain what happens to the moment about point P due to the weight of the sign as it rotates. So this is important. This is a creative question. It's a new question. We have not met this question before. The idea is what happens to the moment about point P due to the weight of the sign as it rotates. How do we calculate that? So before it starts rotating, what is the moment caused by the weight? It's the value of the force itself or the weight itself multiplied by the horizontal distance, because the force is vertical and the distance is horizontal. So what happens as it starts moving in this direction here? So now that it starts tilting like this, and then we have this sign here as well, and the weight still acts in this position here. So what happens then? Of course, the horizontal distance between the weight and the P increases dramatically. So therefore, the moment about P is going to increase as well, because the value of W is the same, but the distance has increased. So therefore, the moment increases as well. And this brings us to the end of our video. I hope this has been beneficial. Thank you for watching.